Hi, welcome back to my channel. In the last video, I talked about basics of CBCT, and then in this video, I'll talk about the artifacts that occur in CBCT. So first of all, you should know that there are four categories. So the first one is the inherent artifacts. Then we have the next is the patient related. No, first we'll talk about procedure related. So procedure related. Then you can talk about introduced artifacts. Introduced artifacts, and the last one being patient related. Okay, now let's talk about the first the inherent ones. So in inherent ones, you further need to know three. One is the partial volume averaging, then you have scatter, then you have cone beam effect. Now let's just understand what really goes in all these. So first of all, you should know that the scatter is also called as quantum noise. Okay, now in this, what happens is the X-ray photons, they are diffracted from their original path. So what happens is the photons will scatter. Now this will lead to noise, which is the grainy surface of the CBCT. Okay, so if I have to sum this up, so I would say the X-ray so X-ray photons are diffracted from their original path, so they scatter, and after the interaction with matter, they form grainy CBCT. Okay, now I'll just tell you with a picture. So if you have to talk about it, this one, see, understand it through the photograph so that it stays in your mind for a long time. So I'll just put it here. Okay, let's just put it here. Wait, no. So this is our quantum noise. So quantum noises scatter. Now basically it shows graininess by the contamination of the detector by single scatter radiation. Now let's talk about partial volume averaging. Now in partial volume averaging, you see a stepped image deformity. I'm sorry, stepped image image deformity. Now in this specifically, what happens is the voxel size is more than the size of object. Okay, now in cone beam, suppose this is the thing that I'm the source of these rays, and then I am projecting it like this. So this area and this area is the peripheral portion of the scan volume. So this peripheral portion of scan volume will have greater noise. So this is also called as V-shaped artifact. Okay, now let's talk about the procedure related. Now in procedure related, again you have three parts. One is moire, which is also called as under sampling. Then you have something which is circular or ring artifact, and then you have double contours. Okay, now let's understand. So first of all, let me just show you what is a moire. Okay, not this. So this is moire, this is circular, and so let's just understand. So add it here. This is our circular. The next time it is a partial, I think, yeah, beam hardening, that's in the next part. So see, this is our moire. So what happens is in moire there is undersampling. So what happens is there is the number of basis images that I told you, that the 2D forms, right? So number of basis image is less. So this leads to the misregistration of data. which is called as aliasing. Now look at the picture. Now in this picture, what you can see is there is hypo and hyper dense lines. Can you observe? See, one is radio opaque, then it's radio lucent, and so there is an undersampling that occurs. Okay, let's just go through the text. So Moir artifact, it is too great an interval between bases, so or incomplete scanning or missed registration can lead to the known as aliasing. On the computed cone beamed image, particularly on the periphery, fine alternating hyperdense and hypodense stripes appear to be radiating from the edge of the volumetric data, resulting in the Moir pattern, a type of aliasing artifact. Now let's talk about circular ring. Now this occurs due to defect of scanner, or it can be procedure. Basically it's procedure related, right? So, or it can be because of the imperfection within scanner, or it can be due to poor calibration. Okay, now look at it. This is the circular ring defect. Now this is the appearance of the scanner related artifact of circular rings because of the imperfection in the scanner detection as a result of poor calibration. Now let's talk about double contour. Now in double contour, what occurs is there is a misalignment of source to detector. Therefore, components need to be periodically realigned. Okay, now this is also due to patient motion related. So here you can also mention double contour. Now in introduced artifact, there is one thing that you need to be clear about, that is beam hardening. Okay, so beam hardening, just understand it through a simple diagram and then we'll see if it's easy or not. So see, suppose I have some low energy photons. Okay, so I have low energy photons are absorbed, so the mean energy of beam increases. So this is what is called as the beam is hardened. So this is beam hardening. Now this leads to two things. One is the cupping artifact and one is the white scatter or streaks. Now cupping artifact is distortion of metallic structure due to differential absorption. Okay, now I'll just show you an image of beam hardening that is often asked in the exam. So let's just go through this image also. Okay, so see, this is beam hardening and here we have both cupping artifact and streak. So see, beam hardening, dark bands and scatter, white streaks, and cupping image distortion. Beam hardening you can see in the form of dark bands. Okay, you need to know which is beam hardening, which is cupping artifact. So okay, the white streaks is scatter and this distortion of the image is cupping artifact. Okay, yeah, so this completes all the the artifacts that are seen in CBCT. So yeah, so if you found this video helpful, do give it a like, share, subscribe, and just let me just check once again if I've forgotten to okay, we can also just give me a second. Okay, so I'll just talk about these images also once. Nothing yet. So in patient related, you can have this photo started here. So see, motion related, so the patient moves during the scanning procedure can result in misregistration artifacts which can appear as double contours in reconstructed image as shown in Excel and C. So here you have, right, can you observe there's double contouring, right, and double contouring. So yeah, this is the patient related. Now this is just the certain phases that occur during processing. Basically in this you have to talk about the offset and the gain factor, okay, and this is something which was about the format. Yeah, so this is, I forgot to explain. See, in formatting, either you can have orthogonal projections, which are basically our usual ones, which is the axial, coronal and sagittal, or you can have non-orthogonal, which is the transaxial, which is the serial transaxial. This is used for implants, okay. Then you can have a curved oblique or curved planar. Basically this is the axial section of mandible, if you can see. So in this now you have something called as a planning line or a spline, and then linear oblique is basically used for condyle, okay. So this is our non-orthogonal planes, okay. NPR, multiplanar reconstruction. Then we have something called as volume rendering. Now what do you mean by volume rendering? Volume rendering can be either direct or it can be indirect, okay. So either it is direct or it is these both are indirect. Now in direct you have sometimes called as MIP, okay, or you have RASM. Okay, let's understand. In RASM, sorry, this is the direct, this is the indirect. Yeah, so this is the direct and this is the indirect. Okay, see IVR, right? So let's just go through it. So first of all, what do you mean by MIP? So MIP stands for maximum intensity projection, okay. So just write it, this is indirect, this is direct, sorry. So maximum intensity projection, see what you will do is you will choose a highest voxel size of grayscale value, and then you will say that I just want this particular voxel size only to be shown, okay. I'll just tell you, suppose just for an example, suppose this is our lung, okay, and you have a certain nodule here. So what I am telling is this is suppose 750 value and the nodule is 1000 value, and then I set the setting that I just want the MIP to be more than 1000, more than equal to 1000. So in the image that will be formed, I will just have the nodule being shown and the lung won't be shown, right? So this is what is called as MIP. So if you observe here in MIP, we are selecting certain certain, like we are selecting the bone voxel size that we want to see, right? Basically we are selecting radiography. Then what is RASM? RASM is basically the concept of making other radiographs from one CBCT. See, you had a CBCT here and you formed an OPG, or you can even form a lateral ceph. So this is called as RASM. Fine. Now we just go through the text that's given below. So there are two categories. One is the multiplanar reformation, which consists of linear, curved oblique, serial, transaxial, and volumetric rendering, which is RASM, comprising the images of increased section thickness. Then we have indirect volume rendering, the most common of being MIP. Alright, so MIP is a part of indirect rendering. Then direct volume rendering. Fine. In direct rendering volume, you can have a solid VR or a transparent VR. Suppose I just want to see the solid VR, like I just want to see the teeth. So you can set the setting and then you can observe. So these are the related things. This is basically the processing, right? So if you have 30 dark images and then you will calibrate it, then there's a gain sequence. You have a scintillator which is made of cesium iodide and so on. So now let's just look at these photographs also. Okay, by this you will understand nicely. See, in the RASM images, now RASM, I told you that from one CBCT image you can form another CBCT image, right? So the axial projection is used as a reference data. Section slice is identified which corresponds to the mid sagittal line. Thickness of the slices increase as slab increases. So we can form a full thickness, like we can simulate the lateral ceph. Now this is about MIP. Now selection of single highest for display, and only single is represented. See, okay. So method is produces a pseudo three-dimensional image by evaluating each voxel size and an imaginary projection ray from the observer's eye within the data set, then representing only the highest value. In this example, an axial projection is used as a reference image and the projection ray is identified throughout the entire volumetric data set, each which grayscale, okay. So fat, air, muscle. So in this, basically we just have selected one highest value which is corresponding to the bone or the metal to see the restoration. You get it? So this is what is MIP. Now this is volume surface rendering. In this You are basically selecting an upper and a lower limit of the range of the intensity values to include in the segmentation. The visual result of changes in the scale is represented in real time, so the effects of incremental changes can be visualized. Now in A you can see the bone is being represented, and in B you can see the transparency. Okay, so this is about volume rendering. So this completes the topic of artifacts in CBCT, and I hope this video was helpful. If you found this video helpful, do give it a like, share, subscribe. Thanks for watching.